Yeah, thank you all for being here so late on the last day of the festival. So yeah, if you were hoping to hear how to make a random number generator, you are out of luck, because this is a talk of how not to make one. So I will share with you some stories from history of what happens when randomness fails or when a random number generator doesn't work. So maybe in the end you can just do the opposite of everything you hear in this talk. So the first story takes place at the Sumo robot tournament. It's an incident that inspired me to give this talk. So in case you don't know, at the Sumo robot tournament, everyone shows up with a small robot. There's a weight limit of, I think, 1.5 kilos. Robots have to fight each other. They have to push other robots out of the field, and of course they have to ensure that they don't get pushed out themselves. Robots themselves are very simple, so they have some motors, some wheels to move around. They have some sensors to detect that they are still on the field, to detect other robots, to know to charge at them. And there is a little Arduino board that controls the whole thing. So basically the creative part is you write your C code that is executed during the fight. The design of these robots is not necessarily very interesting. So robots basically need to be short and stable. They need to be very close to the weight limit, as close as possible, because there's no clever strategy that can save you from the opponent that's somewhat heavier. So yeah, they need to have some protection for their wheels. They need to be shielded so that it's not easy for other robots to slide underneath and flip them. So a friend of mine was participating in one of these tournaments with this robot that you see in these pictures. The robot is called Phoenix 2. I did not ask what happened to Phoenix 1. Presumably it burned into ashes. But Phoenix 2 had a very clever design of the front blade. So in this bottom picture, maybe you can see that it has a metal plate in front, and you need something metal in the front if you're going to go face to face with other robots. You need something that will not bend or deform or break. But the clever thing that my friend did is he put a thin piece of plastic on this board, on this blade. So on top of the metal blade, there is just a regular folder, plastic from a folder, and that it's very thin, so it bends, it hugs the surface, and it can easily slide under another robot and flip it. So this tiny change, in addition to everything else done correctly, is what got him into the final of this tournament. And the reason I say got him into the final is because he actually did not win in the final. So here's what happened. Here is my diagram. So the other finalist was observing the previous rounds, and he noticed a pattern. And the pattern was that at the beginning of each round, Phoenix 2 first charges forward to the middle of the field, and if it doesn't find another robot, it always makes the left turn. So it was always to the left. So what the other finalists did is, the rule of the Sumo robot tournament is that you start from the opposite sides of the circle, but you can angle your robot any way you like. So what the other finalist did is he angled his robot to his right, and he held on to his robot for an extra second after the whistle. So he waited for the Phoenix 2 to move to the center of the field, and then made a left turn, and that's how he was able to attack him from the side, because on the side was the weak point. So maybe it would be considered cheating that he waited for an extra second, but yeah, either way, it would not be possible to exploit this pattern if the pattern was not there, if, for example, Phoenix was moving randomly left or right. So here is the root cause of the whole thing. So sometimes robots need to make decisions. In case that they don't find another robot and they're still on the field, they need to decide which direction to move. And that decision needs to be based on some sort of randomness, ideally. So my friend was aware of this, and he made a pseudo-random number generator that he encoded in C. So it's something like this. It starts with a hard-coded constant. It applies some mathematical operations to transform this constant into something else, and then transforms it again. And if you look at all the numbers that are generated, they will look very random. They will pass all statistical tests. And then he will use this number in other functions to make decisions. So yeah, it's all very clever, but of course, when you start your round, when you start your fight, the code starts executing from the beginning, so it will always start from the hard-coded constant, and the first decision it makes will always be the same. So because it's just computation, the starting point will always be the same, all decisions will always be the same. So yeah, that's how my friend, my foolish friend, lost in the final of the Sumo robot tournament. And there is probably a lesson to learn from this incident, apart from the obvious lesson of don't befriend Sumo robot enthusiasts. They will fill your life with endless frustration. But maybe a lesson related to randomness would be you cannot compute your way into a random number. So whatever clever mathematics you use, if the starting point is the same, everything you do afterwards will be determined by that starting point. Everything will be deterministic. But enough about my foolish friend. Other people have made similar mistakes. And some of these people were designing game shows in the 80s. So in the US, in the early 80s, there was a popular TV show called Press Your Luck. And the contestants would compete in the studio. They would play with boards that looked something like this. So these fields would have various cash prizes. And there would be this glowing frame jumping from field to field, and all a contestant would need to do is press a big red button to stop the field from moving to get their prize. And the content of these fields also changes, so they could win some cash prizes. Some of these fields have a plus sign next to them, which means you get the money and you get to play again to get even more money. So in 1984, a gentleman named Michael Larson participated in this quiz, and he kept winning more and more money. I think it was 24 rounds of winning the cash and the extra spin for the total amount of something over $120,000, which was a lot of money in the early 80s, I think. I think you could buy a house in London at that time, so boomers in the audience will remember. So when they investigated what happened, they found out that Michael Larson was actually studying the patterns on this quiz show, and he concluded, he reached two important conclusions. First, perhaps I forgot to say an important thing. So this game is not entirely risk-free. So there are these death fields. So if you land on one of these deadly fields, you lose all the money you've accumulated so far. So yeah, what Michael Larson noticed is that there are two fields on this board which will never give you a death field, which will always give you a cash prize and the extra spin. And another thing he noticed is that the pattern in which this frame is moving is not entirely random, so there are only two possible paths that this frame can take. And yeah, he was able to follow it and to memorize the pattern and to anticipate when it will land on one of these two safe fields. So yeah, that's how he won a lot of money. And yeah, perhaps there is a lesson to learn from this story. If you are a game show creator, perhaps don't confuse pseudo-randomness for randomness. If it just looks, it's not enough that it looks random, it's possibly necessary that it is truly random, or at least in a way that people cannot compute. Even though I have to say I like the idea of patterns being predictable, then it becomes a game of skills rather than a game of luck. Moving forward to the late 90s, back in the day you could play poker online and you could even cheat, or some people have found a way to cheat in online poker. And yeah, the poker game actually used a very good random number generator. So the random number generator was seeded from a network traffic. Now that network traffic is something that we call a non-physical true random number generator. So it's something that like no one can compute. It depends on so many different actors, and in general, even though it doesn't come from some physical process such as alpha particle emitter, it is still it is still impossible for people to compute. However, the mistake that they made is that they mixed entropy into a 32-bit number, and and then used this 32-bit state to shuffle the cards. You may already know that there are many ways to shuffle a deck of cards, 52 factorial to be precise, approximately 2 to the 225, a huge number. But of course, using a 32-bit state, you can only get 2 to the 32 possible poker games or possible shuffles. So how does that help you? Well, in the first hand, you will get five cards. So well, let's do some math. Let's start with these 2 to the 32, which is approximately 4 billion combinations. There are 52 possibilities for your first card, so that reduces the number of possible shuffles to something over 80 millions. You also have a second card, third, fourth, fifth. You end up with around 14 possible shuffles. And in poker, you can actually replace some of your cards. So once you ask to replace one card, you will know exactly the arrangement of cards in a deck that you started with. So you will know exactly which cards your opponent has, and you will know exactly when to fold. So here the problem was not that the random number generator was bad. It's really that they artificially created this bottleneck of 32 bits. So yeah, that's maybe a lesson here. Avoid the bottlenecks. And in order to tell you about the next incident, I have to give a crash course in cryptography. So it will only take 1 minute. So there is something we call public key cryptography. It is used in all types of digital signatures, of authentication protocols, things like what your browser uses to know it's talking to a correct website. And all public key schemes are based on mathematical problems that are easy to solve in one direction, but very difficult to solve in the other direction. For example, I give you two large prime numbers and tell you to multiply them. Should be very easy. A smart 10-year-old will probably do it in a couple of minutes using just pen and paper. But if I gave you a product of two large primes and told you to find to factorize it using just pen and paper, it will take you, better part of the day, I think, to do that. And you scale it up sufficiently, and you end up with something like RSA, which works with very large prime numbers. They would be at least 300 decimal digits written down. And in that case, computers can multiply these numbers very easily, but they cannot factor these large products, even if you have all the computing power in the world and you run it for hundreds of years. However, there is a shortcut. If I gave you two of these numbers and told you that they share a factor, then you could use something called Euclid's algorithm. And it's a very simple algorithm. Some of you may have learned about it in school. So it's basically an algorithm for finding a greatest common divisor. So you start with these, this is like a visualization of how it works. So you start with a rectangle whose sides are these two numbers, and then you remove the squares from the shorter sides until you end up with the smallest possible square, and the side of this square is the common divisor. So it's very important when you generate your RSA keys. They are public keys. So public keys, these products are available to anyone. So it's very important that different keys, they don't share the same prime factor. Otherwise, they can be trivially broken. And if you generate your RSA keys in a random manner, you will not have this problem. So probability is on your side here. But is this something that actually happens? So there were two large-scale studies that examined various web certificates. They found all sorts of terrifying things. Among other, they found this class of devices that was always that had generated many certificates, and they all shared the same prime number. One of the factors was always the same. And when they root caused it, they found first that they used OpenSSL, which is a secure library, but of course it has to take its randomness from somewhere. In this case, it took it from a Linux pseudo-random number generator, which was seeded by time. And unfortunately, they did, at the very beginning of each procedure, they did this step, which simply reset the system time to 0. Interesting thing, like why did this produce so many factors where first number is always the same, but the second is different? We can only speculate that it used some procedure like this, where it first resets the time, seeds the RNG with that time, generates the first prime, which is a very long procedure, seeds the random number generator with the new time, and then generates the second prime. And there is probably some clock drift between these two procedures, because they are cheap devices. This is my cue to check the time. I think I don't have time to tell you about other incidents, but there are many of them. Let me just leave you with one lesson. We want our hardware and software to be reliable, and in most cases, reliable means that it's predictable. In fact, in all applications other than generating randomness. That's what you want. You multiply two numbers. It would be weird if you got different results. But for random number generators, you want them to be reliably unpredictable. So that's why you have many enemies, the worst of which is your intuition. You may be thinking, oh, I use this alpha particle emitter, and it is enough for me to generate randomness, but perhaps you've accidentally created a bottleneck, perhaps you've accidentally removed the entropy. So yeah, in case you ever need to make a random number generator, please do everything opposite of what you heard today, and you'll be fine. Thank you.